All right, one more concept and then we'll do some examples. I want to introduce the notion of a subgraph. A subgraph is kind of like a subset, but there are a little bit more conditions imposed. So a graph, of course, is a set of vertices together with a set of edges together with an appropriate assignment. So let me just, by example, make a drawing of a graph and talk about its subgraphs. Okay, here you go. This is a graph on, let's see, 5, 11, 12 vertices, and we've got various edges in it. So it is one graph, just sort of all together. And what a subgraph is, I'll draw a couple. What a subgraph is a certain collection of the vertices. Let's say these vertices, and a selection of edges amongst those. You don't have to sort of select all of them, but we're going to collect together some of them, let's say. So this other graph, we could call it H, is a subgraph of the graph G because it is a graph in its own right. So it is a collection of points and lines, and the lines connect together, pairs of points. Here and here. And it coincides completely with a subset of G. So H is a subgraph of G. Now, the following is not a subgraph of G. If I go like this is not a subgraph because it's not even a graph. You can't have this dangling edge right here. You have to select some vertices and select some edges that connect them. There's a couple special subgraphs of any graph. So given any graph, the empty graph is a subset of that graph. It is the selection of none of the vertices and none of the edges. And in fact, the empty set is a perfectly good graph. I probably haven't mentioned that before. And then if you have a graph and you take the entire graph as a subgraph of G, that's a valid subgraph of the graph G as well. Okay, let's practice with the concept just a little bit with a question. Here's a graph G. Let's see if we can figure out how many subgraphs of G there are. Well, there's the empty subgraph, as I mentioned before. And then why don't we organize our count of subgraphs depending on how many vertices they have. So let's number the vertices like this. And let's enumerate all of the graphs that have only the vertex V1. Well, that would just be the V1 graph like this. I might use some colors just to enumerate them, make it a little bit easier. So that little singleton isolated graph that just consists of V1 is a perfectly good subgraph, right? Okay, and then I have the others as well. V3 standing alone is a subgraph, and V2 standing alone is a subgraph. So they're just boring little subgraphs. Okay, let's count the subgraphs of that have 2 vertices in them. So I could have a graph that consists of the vertex V1 and the vertex V2 and does not have an edge in between them. Or I could have the vertex V1 and the vertex V2 with an edge in between them. These are both subgraphs that have the vertices V1 and V2. Yeah? Okay, let's look at the other possibilities. You've got V1 and V3 together, okay, with V3 here. And the possibility is that you take those 2 vertices alone, or you take it with an edge. And then finally, there's only one way I can make a subgraph that consists of the vertices V2 and V3, and that's V2 and V3 without an edge. There is no edge in G. So this would be a subgraph consisting of 2. And then we're going to have some graphs that consist of all 3 vertices. So let me color those three and copy them in case I need them later. Okay, so G itself is a subgraph of itself. And then we could, of course, have all three vertices with only this edge selected or something. And then we could have all three vertices with the other edge selected. And then we could have all three vertices with none of the edges selected. Okay, so I think I have them all. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And I'll just say that many of these subgraphs look alike, right? Like these three subgraphs as like geometric objects or graphical objects, right? They're exactly the same. They're just like a one isolated point graph. These three graphs look the same. These two graphs look the same. These two look the same. And then these are sort of oddballs by themselves. Okay, so that's the idea of a subgraph. There's a lot of subgraphs of any given graph. Well, depending how big the graph is, there could be lots and lots of subgraphs. Okay, I wanted to do a couple more examples involving the degrees in graphs, if I can get this to scroll properly. All right, let's think about these questions. So we're going to use a graph to model the question. In a group of 25 people, so you can imagine the people as vertices, right? I'm not going to draw all 25 dots, but imagine there's 25 vertices like this. Is it possible for each person to shake hands with exactly 3 other people? So let's say this guy shakes with those 3, and this one, well, he's already shaking with this guy, so maybe this one, and so on. Is that possible? Well, what it's asking then is there a graph on 25 vertices where each of the degrees of the vertices is 3, right? Because if you're modeling handshaking by drawing an edge between 2 people, then asking whether or not you could have each person shaking with exactly 3 others, you're asking for the vertices to have each degree 3. So I think the answer is no. I hope you agree, because remember, the total degree of a graph has to be an even number. And if you had a graph on 25 vertices, each of degree 3, that would make the total degree of the graph 75. And a graph cannot have an odd total degree. Okay, what about this one? In a simple graph, remember that's a graph without parallel edges or loops. In a simple graph, must every vertex have degree that is less than the number of vertices in the graph? Let's think about it. I like to draw examples to think about these questions. So let's say I have a graph on 5 vertices, for example. If it's simple, so no loops and no parallel edges, can it be the case that some vertex has a degree that is the number of vertices in the graph? Like, could I have it so that this vertex has degree 5? Well, no. We've actually thought about this concept in a previous example. The maximum number of edges that could be attached to any vertex is the number of other vertices in the graph. And if there's, let's say, n vertices in the graph, there are only n minus 1 others. So that's how I'm going to explain it. Okay, so there's my explanation of why in a simple graph, every vertex must have degree strictly less than the number of vertices on the graph, in the graph. Can there be a simple graph that has 4 vertices and each have different degrees? So let me draw and then answer. This should be scratch work. If we're looking at a simple graph again, then we've just decided that each vertex must have degree that is strictly less than the number of vertices total. So we're talking about the numbers 0, 1, 2, 3, in this case 0, 1, 2, 3. And so I had to ask myself, can it be the case that each of these 4 vertices have different degrees, in which case it would have to be 0, 1, 2, and 3. Well, there's no like even odd problem here. Like 5 plus 1 is 6, which is an even number, so presumably it might be okay. But when I start to try and draw the edges, I run into a problem. So like, for example, if I'm going to try and get this vertex of degree 3, I need to attach 3 edges at that vertex. I can't draw a loop and I can't draw a parallel vertex, so I would be forced to connect it like this. So I guess it cannot happen. Let me argue that in a sentence. Okay, and for part C, can there be a simple graph that has n vertices, all of different degrees? It's actually exactly the same argument that I just went through, but for a graph on n vertices instead of 4. So same argument as B, the answer is no. I'll say similar. You have to change the 3 to an n minus 1,